Hello everyone. Today I am going to reproduce the same thing that I have taught in the class in the form of video lecture. Let's see where the today's class falls. After like there were these class already taken, like introduction, roots of drug administration, and pharmacokinetics, absorption and distribution by transformation, and now my section has come, that is excretion, and next two classes will also be taken by me. So let's begin. Now where are we? Look, for any drug, that is except for the drug that is given by intravenous route, one thing happens, that is absorption. Absorption is the drug getting into the blood. The drug administered through any route get inside the blood is absorption. Absorption takes place, and after absorption the drug gets inside the blood, and from the blood it gets distributed to the different sites, like sites of storage or sites of action, and this process is known as distribution. And yes, the drug works in our body only for some time. It will not last in our body forever, because it will at last be degraded by metabolism or by transformation, and the degraded products or the metabolites are removed from the body, and at many times unmetabolized the drug may be removed from the body by the process known as excretion. And there are various paths of excretion. These are urine, the most important path that comprises of bulk of today's class, and bile, feces, sweat and saliva. This is excretion. So overall we have this pharmacokinetics: absorption, distribution, metabolism or biotransformation, and excretion. So excretion, what is excretion? How is it defined? It is the passage out of systemically absorbed drug, or it is the removing of the drug in the blood. Different paths of excretion: urine, the most important path; feces, exhalation, saliva and sweat and milk are other minor paths. So urine, this is the most important channel of excretion of majority of drugs. Now renal excretion, urine, of course it comes kidney, and kidney is the main organ of excretion. It excretes all water soluble substances present in the glomerular filtrate. Water soluble means ionized, polar or non-lipid solubles. These all are almost synonyms: ionized, non-lipid soluble or polar substances. It removes these substances. Now this is what the kidney does. Blood will come into the kidney through the afferent arterioles. This is the afferent arteriole, and blood will get inside the glomerulus, and it has something like the T filter, that is fenestrated capillaries. So from this, especially the many solutes are filtered, like the T is filtered, and along with this many solutes are also go through this filter, through this filter, and reaches this tubules or proximal convoluted tubule, and this process is known as glomerular filtration. This one is known as glomerular filtration. And in this and from these tubules, many things are reabsorbed back, and most of them are reabsorbed substances. Most of them are lipid soluble. All the lipid soluble substances, all the non-polar substances or the hydrophobic substances are absorbed. Around 99% of them are absorbed, and this process, this 2 is known as reabsorption, and this happens by passive diffusion that we'll be talking later. And besides that, many things are secreted back inside the tubules to be thrown away in the urine, and that is known as secretion. So overall, we have net renal excretion is equal to glomerular filtration plus tubular secretion, which tends to throw the solutes away from the body, and tubular reabsorption, which tends to reabsorb and secrete less thing or throw less thing from the body. So net absorption, glomerular filtration plus tubular secretion minus tubular reabsorption. Now let's look at it more closely. Glomerular filtration. All non-protein bound substances, all non-protein bound drugs present in the glomerulus is filtered, whether it is hydrophobic, hydrophilic, or in other words polar, non-polar, or in other words lipid soluble, non-lipid soluble. Everything is filtered from the fenestrated glomerular capillaries, everything is filtered. And now tubular reabsorption, this occurs by passive diffusion, I already told, and this is the this place comprises of tubules or would be thrown in the urine, and this is the blood or basolateral surface, and this is, and many things are absorbed over here. Many things are absorbed by passive diffusion, and this happens by passive diffusion of, and let's do 99% of lipid soluble drugs in the glomerular filtrate are reabsorbed, but non-lipid soluble, this one, these blue ones, these are non-lipid soluble. So the non-lipid soluble highly ionized drugs are unable to get reabsorbed. Aminoglycoside, a group of drug that you will be knowing in the future. Quaternary ammonium compounds are non-lipid soluble or highly ionized drugs. Highly ionized drugs, polar drugs, non-lipid soluble drugs, this is the same, are not reabsorbed and therefore largely excreted in urine. So are not reabsorbed and largely excreted in urine. That means these ionized substances are not reabsorbed and are excreted in urine. So let's look at it. Ionized drugs are largely unabsorbed and excreted. So why don't we manipulate this fact clinically? We know for the fact that ionized drugs are largely unabsorbed and excreted, and we also know the fact that acid drugs are largely ionized in alkaline urine and basic drugs are largely ionized in acidic urine. Henderson-Hasselbalch equation nicely explain this. Acidic drugs are largely ionized in alkaline urine and basic drugs are largely ionized in acidic urine or acidic medium and basic and alkaline medium. So what we do is, barbiturates and salicylates are weak acids. So if we want to remove them fast from the body, we alkalinize urine because they are acid drugs, so that in alkaline urine they ionize and are not reabsorbed, and those are largely excreted from the body. And similarly, excretion of weak bases like morphine, amphetamine could be enhanced by acidifying urine. But it is not practiced clinically because acidosis can induce rhabdomyolysis, cardiotoxicity, which have often worse outcome than morphine and amphetamine itself. It would be good to excrete them more by acidifying the urine, but acidosis is dangerous. That's why we don't do it practically in clinics. Now, tubular secretion. This is tubular secretion number 3, and for tubular secretion there are two important things. One is efflux transporters that we might have learned before in the pharmacokinetics as well. These efflux transporters are primary active transporters, that is P-glycoprotein, and another is non-specific transporters, organic acid transport proteins or transporters and organic cation transporters. These are secondary active transporters. I hope you know by now what is active primary active transporter and secondary active transporters. Now, these tubular transport mechanisms are not well developed at birth. As a result, duration of action of many drugs, example penicillin, cephalosporin, aspirin, is longer in neonates because they are not excreted by these active transporters. So, regarding P glycoprotein, these are encoded by multi-drug resistant 1 gene. The P glycoprotein, this is P glycoprotein, this is lumen of proximal tubule, and it is located in the luminal side, as we can see. This is encoded, this is a protein, this is a carrier protein, so it has to be encoded by a gene, and the name of that gene is multi-drug resistant 1 gene. And this PGP, as we can see, is located in the luminal membrane of the proximal tubular cells. Luminal membrane of proximal tubular cells. So these are also, besides in the intestine, besides in the tubules, they are also expressed elsewhere, where also they pump out many drugs and metabolites. And this P glycoprotein can be induced or inhibited by different drugs. For example, quinidine decreases the excretion of digoxin by inhibiting the efflux carrier P glycoprotein. That is, P glycoprotein is normally excreting or effluxing or pumping out digoxin, and this process is inhibited by quinidine. That is the inhibitor of the P glycoprotein. That's why the level of digoxin in the blood increases. Now, organic acid transport or organic cation transport or organic base transport. Organic acid transport, the name suggests that it will transport the penicillin, probenicid, uric acid, all the acids. And organic cation transport, it will transport all the bases. For exogenous substances, that is drug or the substances administered from outside, or that is not normally present in the body. For exogenous substances, secretion into the tubular lumen predominates. The thing we have to remember that these non-specific transport protein, they not only secrete, they can also reabsorb. They are bidirectional. And for the exogenous substances, like I have already said, that is exogenous substances that is administered from outside the body, the secretion into the tubular lumen or secretion into tubular lumen predominates, whereas endogenous substances like uric acid is predominantly reabsorbed. For example, organic acid transporter secretes the penicillin and it reabsorbs the uric acid, because penicillin is exogenous and uric acid is endogenous. So, manipulation, drugs utilizing the same active transport compete with each other. So, what we do is we can use probenicid. For example, we can use probenicid, which is an organic acid which has high affinity for tubular organic acid transporter. So, it blocks the active transport of both penicillin and uric acid. With the effect, the plasma concentration of uric acid decreases and penicillin increases, because penicillin is normally secreted and uric acid is normally reabsorbed. It blocks both the process, thereby decreasing the uric acid and increasing the penicillin. That's why it may be used to enhance the effect or plasma level of penicillin, or it may be used to decrease the uric acid in the blood. That is known as uricosuric drug. Now, we are done with the urine. Now we will come to the feces. Orally administered unabsorbed drug. Orally administered but unabsorbed drug like heavy metals and few laxatives like anthracene purgatives are excreted by feces. Drugs secreted in bile. Example, many organic acids, organic bases, Lipophilic drugs, steroids, larger molecules with molecular weight more than 300 are excreted via feces. Many of them. Exhaled air, gases, volatile liquids like general anesthetics, alcohol are eliminated by lungs. Besides, lungs also serve to trap and exclude any particulate matter. For example, those who take crack cocaine intravenous, they may inject the particulate matter, and that when it reaches the lungs in the pulmonary circulation, the lungs might trap it and exclude it. Saliva and sweat, potassium iodide, rifampin, lithium, heavy metals are those metals heavier than sodium, are excreted in saliva and sweat, and quite understandably most of the drugs in saliva are swallowed and meet the same fate as orally taken drugs. Regarding milk, it bears significance to suckling infant, which is not difficult to understand, I suppose. And lipid soluble and less protein bound drugs are more likely to reach milk. Lipid soluble because it will go by passive diffusion, less protein bound drugs because through filtration as well, as we can see in the glomerular filtration. Though total amount of drug reaching the infant through breast milk is generally negligible, we administer drug to a lactating woman only when it is absolutely essential, because we don't want to take chance. We don't want to harm the baby at any cost. Thank you.